A box with an open top is to be constructed from a square piece of cardboard, 3 feet wide, by cutting out a square from each of the 4 corners and bending up the sides. Find the largest volume the box can have. All right, so step 1 was to read the problem. Step 2 is to draw a picture. So let's go ahead and draw a picture. So we have a box with an open top. That means it has no lid. It's going to be constructed from a square piece of cardboard by cutting out a square from each of the 4 corners. So this is the piece we're going to cut. And then if you could imagine folding up the box, then this would become the center of the box right here. And then these would become the edges of the box. So it would make a little box folded up. So there's a couple of things that we need to recognize here. When we're looking at our box, it says that we have a square and it is 3 feet wide. So that means from here all the way over to here is 3 feet wide. But if we look at this, we're going to cut a piece out of the corner. Well, that piece, we don't know what that is. I'm just going to call it X because that's our unknown. But it says that you're cutting a square out of the corner. So each of those little side dimensions there are going to be X. But it says that this is a square. So you know that this outside is also 3 originally before you cut these little pieces out of the corners. So what can we do with this? Well, first of all, let's see if we can find some sort of an equation. We drew a picture, we assigned some variables. Let's see if we can create an equation. What is it asking us for? Find the largest volume. So it's asking us for volume. So let's see if we can start with something to help us get to volume. So volume is length times width times height. Well, let's look at this. What do we have? We know the length is equal to the width in this case because they're squares. Now, these are not 3 each because remember, we're cutting out these corners. So if you cut out a corner from this side, then that's going to be a width of X. And if you cut one out from this side, that's another width of X being removed. So both the length and the width are going to actually look like that original 3, and then you're going to be subtracting 2X. 1X from this corner, 1X from this corner that you have cut out. So we're making some progress here. Now, as we fold the box up, so if you can imagine folding this piece up right here, it's going to be this tall. It's going to be as tall as the side of the square that we cut out. And that's what we just labeled as X. So in this case, our height is going to be X. Well, let's take all of this and let's put it into our equation. So we know that volume is length times width times height. In our case, the length and the width are both 3 minus 2X. So it would look like 3 minus 2X times 3 minus 2X times our height of X. This is a little complicated to write, so I'm just going to shrink it down by using my exponent so I don't have all of these different pieces. I really don't want to have to use the chain rule and the product rule, so let's see if we can multiply this together. So 3 squared is going to give us 9. 3 times 2X is going to give us 6X, and then we have it again. 3 times 2X is 6X again. So that's going to be 12X. They're both negative, so let's do our 12X. Then we have negative 2X times negative 2X, and that is going to give us positive 4X. Now that is just this piece here squared. We still have an X to tack on. So this would have been 4X squared. So that's going to become times X, and that's going to give us 4X cubed. This would have been minus 12X originally. So we're going to multiply that times our X, which is going to give us 12X squared. This was 9X, but we need to distribute our X. So that's, it was 9. We need to distribute our X. So that's going to become 9X. There we go. So multiplying all of this out, and it looks like we get 9x minus 12x squared plus 4x to the third. So we've gotten an equation. Next thing, we need to take our derivative and we need to set it equal to 0. So our derivative, what is our derivative going to look like? Well, 9x, so the derivative is 9. 12x squared, so bring down your power, subtract 1, so minus 24x. And then 4 times 3 gives us 12. Bring down your power, subtract 1, 3 minus 1 is 2. We took our derivative, now we need to set it equal to 0. As I set this equal to 0, I notice that all 3 of these are a multiple of 3. So I'm going to pull a 3 out. If I pull a 3 out, that's going to leave me with 3 minus 8x plus 4x squared. Divide both sides by that 3 and it will go away. We need to factor, and a lot of times it's tricky to factor when the highest power is in the back. So I'm just going to switch this around, just rewriting it. Make sure if you rewrite it, the signs all stay. 4x was positive, it stays positive. Minus 8, positive 3, positive 3. So we're okay. So now we need to factor this. You can factor using any of the different factoring approaches. You can factor using guess and check, but we need to factor this. So if we factor this through, it'll look like 2x minus 3 and 2x minus 1. So now we can take both of our parentheses, both of our terms, and we can set them equal to 0. So we took the derivative, we set it equal to 0, and now we're solving. So here we'll add 3 to both sides and then divide by 2. So it looks like x is equal to 3/2. And over here we'll add 1 to both sides, divide by 2. So it looks like x is equal to 1/2. So what we have now is 2 potential different situations where we could have our maximum volume. So we need to check both of these back into our original equation to see which one is better. So let's check our 3/2 first. So if x is 3/2, what's our volume? Well, if x is 3/2, let's put it back in this one. Then that means our volume would be 3 minus 2 times 3/2 squared times 3/2. Well, let's see what we have here. This 2 and this 2 will cancel. 3 minus 3 goes to 0. 0 squared is 0, so the volume is 0. So that's not a whole lot of volume. 3/2. 3/2 is 1.5. And what's happened here is your x, your corner that you've cut out. So here's our bottom, just the bottom piece. The corner that you've cut out is going 1.5 in from both sides. So what's happened right now is the corners have met each other. So that in this case doesn't make sense for the context of our question. It doesn't make sense to have a box with a volume of 0. In other situations, that might make sense. In this situation, it doesn't. So let's try our x being 1/2 and see what we get for our volume in that case. So if x is 1/2, then that means our volume becomes 3 minus 2 times 1/2 times 1/2. Don't forget your squared right here. And if we multiply that all through, it looks like we're going to get 2. So again, this 2 and this 2 are going to cancel. 3 minus 1 is 2. 2 squared is 4. 4 times 1/2 takes us back to 2. So this means our volume would be 2. So it looks like in the case that we are presented, the context of our questions, when x is 1/2, we are going to get our greatest volume, and that greatest volume will be 2. It would be feet cubed as our unit. Let's look at another one. If 1,200 centimeters squared of material is available to make a box with a square base and an open top. Find the largest possible volume of the box. So this one doesn't say anything about cutting pieces out of the sides to make our box or anything like that. So think of it as if you had a flat sheet of cardboard, and from that flat sheet of cardboard, you were cutting different pieces and standing them up to make the sides, and then the remaining piece would be the bottom. So we're assuming a couple things here. We're assuming that we are using the absolute best allocation of our materials. There's no waste. So there's a lot of assumptions being made, but we can follow through with the given information and we can work on solving it down. So here we go. So you have 1,200 centimeters squared. That's an area. See right there, centimeters squared of material. So that means we have a surface area. We're using that material to make the box with a square base and an open top. Find the largest possible volume. So there we go. We have surface area information and we have volume information. So how can we draw this through? Well, I'm not very good at drawing 3D figures, but let me give it a try so that we can see what we're working with here. Here we go. So there's our box. Now let's label what we know. So the bottom is supposed to be a square. So we'll just pretend that it looks like a square, but we'll label it to make it a square. So B and B. The height is right here. And I think that's about all we're given. So the surface area. Do you remember how to find surface area? Surface area is the sum of all the side areas. So let's do this in one piece at a time. So let's do the bottom. The bottom would be our base, which would be length times width, so B times B, so B squared. Plus, now we have all of our sides. Well, because these sides are the same, these sides standing up will also all be the same. So we have 4 of them. So 4, and then the area of one of these sides. So I'll just shade in one right here. So this back side right here. The area would be base, which is B, times height, which in this case we labeled it as H. So 4BH. The B stands for the base, the H stands for the height. All right, we know that we have 1,200 centimeters squared of material. So 1,200 is equal to B squared plus 4BH. So we got that started. We can't really solve for B in this one because we have B squared and we have just B. If I factored a B to the front, that wouldn't help because there'd still be a B stuck inside. So instead, let's solve it for H, because remember, when we get our volume equals length times width times height, we're going to need to make it so that we only have one variable remaining. And we know that in this case, the length and the width are both B. So our H is going to cause us some trouble. So let's see if we can solve this equation for H in terms of B, so that when we go to find our volume, we have only variable B. We can do that. Let's see here. So we'll have 1,200. Subtract our B squared, so that'll move that over, and that'll equal to 4BH. Then we need to divide both sides by 4B. And now we've solved it for H. You could split this apart. You could try to simplify it. I'm not going to worry about it for right now. I'm going to put it in and see what happens. And if I need to simplify it later, I will. So what do we have here? We have B squared times H is 1,200 minus B squared all over 4B. Well, it looks like I can cancel this squared with this B. So that helps just a little bit. And then I have V equals, so this 4 right here is going to look like 1/4 in the front. We have the B from right here, and then we have 1200 minus B squared. Well, that helped a little bit. Let's see if we can distribute. So that'll give us V equaling 1/4 of 1200 is 300, and then we have the B tagged along, so 300 B. And then we have 1/4 B times negative B squared, so negative 1/4 B to the third. All right, we're making progress. Let's take our derivative. So the derivative of 300B is just 300. Bring down your power, so minus 3/4. B, subtract 1 to the second now. So once we take our derivative, we set it equal to 0. So 0 is equal to all this. So if we move our 300 over, and now we need to simplify this down. So at this point, we need to flip and multiply. So this will look like times 4 over negative 3. So if you look here, your 3's are going to cancel, so that would become 100. Your negatives are going to cancel, so that would be positive. 4 times 100, we get 400 is equal to B squared. So we can take our square root, and if we take our square root, that means B could be positive or negative 20. But it wouldn't make sense for B to be negative 20 because remember, B is the length of the sides here of the base of our box. So a length of negative 20 just doesn't make sense in the context of our question for now. We don't always just throw out the negative. Sometimes the negative is what we need. Sometimes that's what makes sense in context of the question. For this one, we're looking at a side length. The negative just doesn't make sense in the context of the question. But we're not finished yet. We figured out our side is 20 centimeters. But that wasn't what it was asking us. It's asking us to find the largest possible volume. So we need to figure out the volume when we have our B of 20. So we got to put it back in. So volume equals, and we have our volume formula right here. So we can put all this back in. We have our 20. And we have our 1200. And we have 20 again. And we have all over 4. So if you remember, we canceled our B squared and our B right here, and then we put it right back into this one. Yes, you could have put it in here. That would have worked as well. You even could have put it in here. That would have been fine also. You cannot put it into the derivative because we've already taken the derivative and we need the original V value. So then if we type this all in, solve it down through, we have 1200 minus 400 divided by 4, and then times 20, and we'll get V is equal to 4,000. And because it's a volume, we'll have centimeters cubed.